system with the z-axis out towards us. This is the point that we're doing the calculation for. This is the point P. The acceleration is equal to negative 10.65, positive 42.40. And so now we're going to do it with a rotated coordinate system with the x-axis this way, y-axis this way, and z will still be the same. So there's x, y, z. What? Yeah, same origin, and then we'll do it one more time with the origin somewhere else. So the origin is still here. That red dot there. Okay, so is the origin accelerating? Okay, that's good. Yep. But the coordinate system is rotating. And so the acceleration of that point P, we're going to get as the observed acceleration of P plus capital omega dot crossed with the position vector plus 2 times capital omega crossed with the observed velocity P plus capital omega cross quantity capital omega cross P. And so we know that's where it's all coming from. We just have to fill in those terms. Well, what do we know so far? Let's get the easy ones first. So first of all, our coordinate system is rotating with that arm. Okay, so the rotation of the... Okay, so if we're trying to figure out capital omega, we have a coordinate system like this. And the rotation of our coordinate system is, according to the right-hand rule, down. So this is our capital omega vector, and it has a magnitude of 5. And these angles are all 45 degrees. So omega is equal to 5 times a unit vector. If you want to go from the positive x-axis to that vector, you can go clockwise, negative 90 plus 45, so negative 135. Negative. And that gives you negative 3.535, negative 3.535. Boom! Yes. It's a great start. And then omega dot is 0. That's just how I do it. And how about the position vector? Well, now in this coordinate system, the position vector is easier. It's just, what? Yeah, I didn't give those distances here, but yeah, this length is 1, the radius of that is 0.6. So positive x direction 1, negative y direction 0.6. So that radius is 0.6 meters. And arm length is 1 meter. And now the two harder ones that we have to calculate are the observed velocity and the observed acceleration. So first, the observed velocity. That's going to be equal to lowercase omega crossed with the r vector. Lowercase omega. So now we're imagining this arm being fixed, and we're just talking about just calculating the velocity due to the circular motion of that disk. That rotation is in the positive x direction. So that's just 10, 0, 0. And the r vector, this is here we see a difference between the position vector and the r vector. That is just from the center of that circular motion, the center of the disk, to the point P. So that's just 0, negative 0.6, 0. No, omega. So for lowercase omega, our coordinate system is rotating with the arm. So our coordinate system doesn't see at 5 radians per second rotation. You know, all it sees is the disk spinning around like that. And then like origins don't matter for angular velocity and angular acceleration. We're just talking about how quickly that orientation is changing. So all that coordinate system sees is. I see it now. Okay. The disk is spinning in the y and z direction. In the yeah, it's spinning on the y. Yes. Right. Yes, you see that circle in the YZ plane. That's right. Yeah, I see. I just have okay. And this is the 0, 0, negative 6. And then the observed acceleration is alpha cross r, and that's 0. There's no changes in any of these angular velocities. Plus 10, 0, 0 cross the quantity 10, 0, 0 cross 0, negative 0.6, 0. This one is 0, 0, negative 6. And so altogether that cross product is 0, positive 60, 0. And now we have all the parts, we can just put it together. So A sub P is equal to 0, 60, 0. Plus negative 3.535, negative 3.535, crossed with the position vector of 1, negative 0.60. What? Oh, so yeah, omega dot. Sorry. Omega dot crossed with P. This goes away. And then plus 2 times this one, negative 3.535, negative 3.535, crossed with the observed velocity that we just calculated, 0, 0, negative 6. Plus negative 3.535, negative 3.535, crossed with the quantity negative 3.535, negative 3.535, crossed with the position vector 1, negative 0.60. Okay, so let's calculate that. Oh, you got something else? 37.57, that's what you got too? If two people get the same thing, it makes me feel a lot more confident. 0.5, what did you say, 7? Okay, well. Okay. Well, that definitely matches the magnitude of that vector. But, yeah. Okay, so these don't match, and they should. So what do we have to do so we can compare them? We could compare the magnitudes, but that wouldn't tell us for sure. But what we can do to make sure that they match is use a rotation matrix to express one now in the coordinate system of the other one. So let's take the one that we just did in this rotated coordinate system. And yeah, so if we have this coordinate system and we want to go to this one. Yep, so that's a negative 45 degree rotation about the z-axis. And so the rotation matrix is cosine of negative 45, sine of negative 45, 0, sine of negative 45, no, negative sine of negative 45, positive cosine of negative 45, 0, 0, 0, 1. And that is 0.7071, negative 0.7071, 0, positive 0.7071, positive 0, 0, 0, 1. Yep. Yes. So the acceleration of P in this coordinate system is equal to Q times the acceleration of P in this coordinate system, and you get negative 10.71, 42.40. Yay. Any questions about that? Yeah, by the 22.43, 37.57. Yep, that's right. Okay, so now let's do it one more time. And this time, I'm not going to draw it out all again, but this time let's put the coordinate system up here. Yeah, there is no reason you would sensibly choose the coordinate system here, but sometimes you have to do, put the coordinate system in weird places because your cameras can only be mounted there or there aren't any other better options. So what's going on here now is the origin is accelerating. And the axes are rotating. And so, since the origin is accelerating, we're going to have to use a relative motion equation that says the acceleration of p relative to the ground, which is what we're always trying to calculate, is equal to the acceleration of p relative to the origin plus the acceleration of the origin relative to the ground. And this one, we're still going to use the equation for acceleration in a rotating coordinate system. And then at the end, we just have to add on the acceleration of the origin. So let's first go through the acceleration, assuming that the origin is fixed, but that the coordinate system is changing orientation. Yes, that's definitely the easier part, yeah. Yeah, it doesn't, you can do it in either order. I guess I was thinking, yeah, sure, let's do that. A pro short joke.
I think that was
So acceleration of the origin relative to the ground. So what's the origin doing? It's in a circular motion. The center of the circular motion is, so it's going around like this. The center of the circular motion is 1 times cosine of 45. Oh. So this acceleration is just going to be alpha cross r plus omega cross quantity omega cross r. Let me draw this circular motion. Okay, so there is the circular motion. And we have to figure out this radius. Well, if you finish that triangle, that's just going to be 1 times the sine of 45. So that r vector is, when we have a rotated coordinate system here, so that r vector is going to be 1 times the sine of 45. That's the length of that radius, the magnitude of the radius. And then the r vector goes from the center of the circular motion to the point that you care about. So if you line that up, put the tail of that vector at the origin of the coordinate system, that's going to be at negative 45 degrees. Any questions about that? So this is times cosine of negative 45, sine of negative 45, 0. So that is 0.5. Which way? And then negative 0.5. Right, 0.7071 squared is 0.5. Is that right? There's no angular acceleration. The angular velocity in this coordinate system, what's the angular velocity of the structure that origin is on? Yep, that's right. Negative 3.535, negative 3.535, That's right. Yep. And so the acceleration of the origin relative to the ground is negative 3.535, negative 3.5350, crossed with the r vector, 0.5, negative 0.50. I forgot one, sorry. We're doing the acceleration, so this has to be times the quantity, negative 3.535, negative 3.5350, crossed with the r vector, 0.5, negative 0.50. I get negative 12.5, positive 12.50. Anyone else getting that? Okay, so set that aside. Are we done?
Yes.
No. That's right. That's true. So now we have to do the acceleration of that point P, assuming that the origin is fixed. And so we're still dealing with the changing orientations of all these objects. We're just not dealing with the fact that our origin is accelerating. So now the acceleration of P relative to the origin is equal to the acceleration of P that's observed capital omega dot cross P plus 2 capital omega crossed with the observed velocity of P plus capital omega cross quantity capital omega cross P. Well, now our P vector is simpler than it was before, because instead of the P vector being this vector plus this one, we're just going from this origin to here. The P vector is just 0, negative 6, 0. You know what I mean, Scott. And then capital omega, that's the same angular velocity that that the coordinate system had in the last example we did. So that's negative 3.535, negative 3.5350. There's no time derivative of that. And then the observed velocity. That is the angular velocity of P crossed with the position vector, lowercase omega cross P. What? You're right, it's crossed with R. Damn it. In this case, P and R happen to be the same thing, but yeah, you're exactly right about that. So what's that lowercase omega? Yep, in the positive x. Yep. So 10, 0, 0. R and P in this case happen to be the same. So that's 0, negative 0.6, 0. And that's 0, 0, 6, negative. And then the acceleration of P. Because we're ignoring for this part the fact that, so we're ignoring where the origin is, but we're still dealing with the fact that this coordinate system is fixed to this body and rotating with this body. So that coordinate system is still rotating this way at 5 radians per second. And then, we figured out in this coordinate system, we know that it's that vector is directed down, and we just have to express a vector with a magnitude of 5 in this direction in that coordinate system. So no matter where the origin is on the body, it's changing orientation at the same rate. The whole body has the same angular velocity, same angular acceleration. So that didn't change from the last example when we moved the origin. Okay, and then the acceleration of P that's observed is alpha cross R, that goes away, plus lowercase omega, mass quantity, lowercase omega cross R. And that is 10, 0, 0, crossed with omega cross R, we already know is 0, 0, negative 6. So that acceleration is 0, positive 60, 0. And now we can plug this all in. The acceleration of p relative to the origin is what we're calculating now, is equal to 0, 60, 0, plus 0, plus 2 times capital omega, which is negative 3.535, negative 3.5350, crossed with the observed velocity, 0, 0, negative 6, plus negative 3.535, negative 3.5350, crossed with the quantity, negative 3.535, negative 3.5350, crossed with the position vector, which is 0, negative 0.60.
Yeah.
Okay, so acceleration of p relative to the origin is, say it again, 25.10, and then add it to the other one. So the acceleration of p relative to the ground is 34.9, 25.10 plus negative 12.5, positive 12.50. And so what's that? 37.50. And does that match what we got in the last one, I hope? Yay! Okay. And then rotate the coordinate system, and you get that the acceleration of p is equal to negative 10.7, 42.40. So it's tedious, but it's cool, you know, like you can,
Like cleaning your bathroom really well.
yes, you can keep moving the origin around, keep putting the coordinate system fixed on different bodies, and if you know how to compare these answers, you'll get the same thing in all of them. Anybody have any questions about any of those? I mean, I guess I would say this is a way to, I think it's sort of nice to see how they all work out being the same thing. It was a reminder that even though you get the right answers, if you have different orientations of coordinate systems, you have to do something with that orientation to make the numbers match. But then it's just, yeah, it's just seeing what changes as you move these things around. How does P change? Is P the same as R? How does R change? How does the fact that now the origin is accelerating come into it? You know, that sort of stuff. Oh, yeah. Yeah, I did notice as I was doing it that picture was getting sort of complicated. Well, I just knew that, forget about that disk for now, because we're just trying to calculate the acceleration at that point. Right. So I knew that this is just going around like that, and the circle is just this horizontal circle centered right above here. And so all I needed, and so I know that when the origin is at this location, that our vector is going to go in this direction, which is going to be negative 45 degrees, you know.
Oh, okay, yeah.
And so I just had to get the length of this. So just do the trigonometry. This length is 1, so 1 times sine of 45 gives this length. And then if it's pointing this direction, then that's negative 45 degrees. So I had the magnitude of of 1 times sine of 45 times the unit vector cosine and sine of negative 45. Yep. Yes.
It seems like we're doing a lot of work to keep it in the coordinate system.
Yes.
Is there like a totally different approach?
No. There's really nothing else you can do. I mean, I guess I would say, like, you could reformulate it in a different way, but it would just be kind of undoing Newton's second law. The same way we do this. We go one way with this. I suppose you could probably reformulate it as undoing that for Newton's second law, but this is the approach. Newton's second law says that what's going on, the relationship between force and acceleration for an inertial coordinate system. And so that's like your first step, is getting an acceleration in an inertial coordinate system. The forces you never have to mess with, because the forces don't require time derivatives of anything. So if you measure forces using force sensors in an accelerating coordinate system, those forces are already correct. Yep. I mean, if that particle P was connected to load cells, that are measuring the force, those forces are being measured in a non-inertial coordinate system. But that doesn't matter. You don't have to worry about that with forces, because you're just taking those direct measurements. You're not taking measurements and then doing time derivatives on your measurements. That's where the problem comes in with calculating the acceleration. You're taking measurements in this rotating coordinate system and then taking time derivatives. It's the time derivatives that always cause the problems with rotating coordinate systems. And when I did the astronaut thing, the example that I introduced this with, I sort of glossed over that, but those sensors in the chair, in order to compare the force sensors in the chair to the acceleration of the person, we had used the rotating coordinate system approach to calculate the acceleration of the person. But we didn't have to do anything with those force sensors, because there are no time derivatives in those. Those read in 7.9, and then, well, he'd have to be pretty light, I guess, but and then later they read in 8.14, and then later this, changing in time, and at each instant you just use those values and it's fine. Any other questions? Okay, I think that's about it for rotating coordinate systems. So for Monday, I'll get stuff together for vibrations, and then we'll start with that. Have a nice weekend.